Log on, tune in, find out. Another good idea from Cambridge.
Andreas Ott, who's going to speak on boundary cohomology and Higgs bundles.
Okay, so first of all, I'd like to thank the organizers for giving me the opportunity to talk here in the seminar. And so my talk will be about bounded cohomology. And Higgs bundles. So all this is joint work in progress with Tobias Hartnick. So representations of surface groups into Hermitian Lie groups have been studied intensively from two different viewpoints. The first one is techniques from bounded cohomology of Lie groups, and these have been applied by Burger, Jotzi, and Wienhardt and others to study these representations. And on the other side, Higgs bundle techniques, which have been applied by Bradloff, Garcia Prada, and Goten and others via the non-abelian Hodge correspondence. And the goal of my talk today is to compare these two approaches and study implications directly from bounded cohomology to the Higgs bundle side, and with a particular focus on what is called the Milnor-Wood type inequalities. And the hope is also to get some implications in the other direction. Okay, so let me start now. So we start with a representation of a fundamental group of some Riemann surface into a Hermitian Lie group, where M is a Riemann surface of genus at least 2. And sorry? Oh, I'll define it right now. Yeah. So G is a Hermitian Lie group, which means the following. So first, G is a real Lie group. It's connected, semi-simple, and without compact factors. And most importantly, the associated symmetric space, which is the quotient of G by some maximal compact subgroup K, is Hermitian as a complex manifold, which means it has a G invariant complex structure. And typical examples are the groups SU, PQ, fixing a quadratic form of signature P and Q, and the symplectic group. And there are some more. And so the main focus in this talk will be on this group here. Okay, so I assume most people are not familiar with the bounded cohomology of Lie groups, so I'll start explaining this. We have So let us first recall the continuous group cohomology. It is defined as the cohomology So we always take, as coefficients, we take the real numbers. So it's the cohomology of the following complex, which consists of continuous functions on G with a certain differential. So the complex is given in degree k by continuous functions from G to the k plus 1 into R, which are G invariant. So it's the G invariant continuous functions of the following form. And the differential is the following. So taking a function like that, we can plug in elements of G, k plus 1, and it is given by the alternating sum with a sign, where we plug into F all but one element. So this means the ith element is omitted. Okay. Yes, this is known as the homogeneous bar complex for continuous group cohomology. And now there is a bounded analog of this, and it's the following definition, which is in this form due to Burger and Monod about 10 years ago. So continuous bounded cohomology of G. So the complex now consists of bounded continuous functions. And the differential is the same as above, so these are the bounded functions. Denoted like that. And again, they have to be G invariant. So this is the G invariant bounded continuous functions. And so, as I said, D is as above. Okay, so actually, yeah.
I'm sure you said this, but when you say G invariant, you mean G is acting on the left or by conjugation?
G is acting on the left, yeah. And so this can be done more generally for arbitrary topological groups, but here we focus on our Hermitian Lie groups. And so a particular feature is if G happens to be compact, all these cohomologies vanish, because you can always, by integration, construct a primitive in cohomology for the cocycle.
What is this? Is exactly like cohomology of finite groups, only with continuous functions.
Exactly.
Okay.
Yeah.
Okay.
Yeah. So if you take a discrete group, then it's just the original definition due to Gromov of bounded cohomology of discrete groups. And so up to now, almost nothing is known about these groups, these cohomology groups. So I'll mention the facts that are known later. And so the continuous cohomology is more or less fully understood. And so the question arises if you can find a relation between these two cohomologies, and there is one. So there's the canonical inclusion of complexes. So from the bounded functions into the continuous functions. So this inclusion induces what is called a comparison map. So we denote it this way. This comparison map goes from the continuous bounded cohomology to the continuous cohomology of G. And there's a big conjecture, which is probably the main conjecture in this theory, which is due to Dupont and made it on the ICM 2006. So the statement is this comparison map is always an isomorphism. And so actually Dupont conjectured this some time ago concerning surjectivity of this map, and Monod, he conjectured injectivity. And it's not completely unreasonable to conjecture this.
So it doesn't seem, it seems an obvious conjecture to me.
Yeah. So there is a theorem due to Dupont, Monod, and Burger. They proved that this map is an isomorphism in degree less than or equal to 2, where it's trivial in degree 0. Both groups are 0 in degree 1, so the main part, the interesting question concerns degree 2. And they proved injectivity, and he also some time ago proved surjectivity.
Sorry, this conjecture is true for all groups or only for the Hermitian?
It's proved for groups satisfying this condition, but not the Hermitian, the second one. Just a connected semisimple without compact factors. And you can go even further and study, or as a particular example, you can study SL2R. And in this case, they proved it's an isomorphism in degree less than or equal to 3. And okay. So it's really a hard business at the moment to get some results for this, but so a result we obtained recently was we were considering also the easiest case, which is certainly SL2R. We tried to extend their result using their methods, and we managed to prove that. So this is due to Hartwig. So we proved that is an isomorphism in degree 4. And we think our method can also be extended to cover all degrees, but it's not done yet. And so I only stated in degree 4. And okay, so once you have, or if this conjecture were true, then you are more or less done, because so it's useful because we can compute the continuous cohomology in general, and now I'll only consider the degree 2 case using what is called the Van Est isomorphism. Which is the following map. So it goes from G invariant, 2 forms on the symmetric space to the second continuous cohomology of G, and it can be given on the chain level completely concrete. So we take a representative here, or invariant form, and it's mapped to the following cocycle. So this cocycle, since we are in degree 2, we have to plug in 3 Lie algebra elements, Lie group elements. So it's defined by integrating the form omega over the geodesic triangle in the symmetric space, which is determined by these 3 Lie group elements. We'll see an example later with a picture where, so here, x is an arbitrary fixed base point, right? So we can associate to any form a cocycle here, and then it can prove it's closed, and it gives you this isomorphism. And we can combine now this Van Est isomorphism with the fact that the invariant 2 forms on X are isomorphic to the second de Rham cohomology of the compact dual symmetric space of the symmetric space X. I'll explain this in a second. So where the compact dual symmetric space is defined as the quotient of the dual group, a certain group, a compact dual of G mod the maximal compact subspace. And this group here is obtained if you take the Cartan decomposition of the Lie algebra of G, like that. So you have the Lie algebra of the compact group and the Lie algebra of this and a non-compact complement with respect to the Killing form. And now we can take we can complexify G, and inside there we can take I times P. And if we pass to the Lie group by taking exponential map, then we end up with this compact group. And we'll see this in a concrete example now. So where can I put this? So here's an example. So we take the group SU11, which happens to be this isomorphic to SL2R. So it's the easiest possible example. So in this case, the maximal compact subgroup consists of U1 cross U1 and S of this, which means determinant 1. So the corresponding symmetric space is in this case the hyperbolic half plane, or for our purposes now, the Poincaré disk. And the compact dual in this case is SU2. And so the compact dual symmetric space turns out to be the Grassmannian of lines in C2, which is CP1. And okay, and then we can now apply the Van Est isomorphism and combine it with this isomorphism here. Maybe I should say a word where this comes from. So if we have a G-invariant form on X, you can because it's G-invariant, it's enough to know it's determined if you know it at the point corresponding to 1, right? So to the base point which corresponds to the identity coset, right, in X. And then once we are there, we have essentially a form on P on this Lie algebra, and we can pass to a form on IP, just in terms of algebra, and then we can extend again on this space here, because it's also we can extend it GU invariantly. In this way, we end up with this isomorphism here.
Why is it closed for?
Sorry?
Why is it closed when you extend?
This here?
Well, yeah. I mean,
Oh, because it's a fact that G invariance implies closeness.
now,
Symmetric space.
Right?
oh, I see.
Okay, I should say, yeah.
Is it known that all of this continuous cohomology is finite dimensional? This implies that H2 is finite dimensional, right?
Yeah, it reduces to the usual de Rham cohomology of the compact dual, which is a compact topological space. So.
The continuous cohomology is finite dimensional, but I guess the non-extra bounded one is finite dimensional.
No, this is exactly the big open question.
Okay.
Nothing is known, and if the group is discrete, as far as I know, these can be even more difficult and really big.
There, are you talking about when you say G, the Lie group? I thought you were still.
Yeah, it's a Lie group.
So you're still talking about the Lie
Yeah,
group?
just the Lie group. Yeah. And if this conjecture, once it's established, or if it's true, then we are reduced to we know everything because we know the continuous cohomology, right?
So the continuous cohomology is always what you just described there. So,
Yeah.
so for SL3, what you are saying is that, for SL2, you're saying that it's 0 in degrees 3 and 4. Is that what you mean?
Yes. Yeah, exactly. And we can make this even more. So okay, we can now apply this isomorphism upstairs, and we get that the bounded cohomology of G by this Burger-Monod result is the second continuous cohomology of G, and by Van Est it's the de Rham cohomology of CP1, which is R. So the question arises: what is the? Can we give a concrete generator for this cohomology group? And the answer is yes. It's given by the Kähler class on on the Poincaré disk. So one way to give this is so we can give this Kähler form on D in C explicitly by the following formula. That. I hope I got it correct. Yeah, you can check it's invariant and so on. And now the let me go to another point. So now we apply this machinery I just described. So we take this form and map it to its co-cycle. And now it's very explicit. So we have this plug in 3 points and take the integral over the geodesic triangle. And now if this is the Poincaré disk, so we get something like, say, which looks like that, for instance, right? Depending on these points. And now it's a well-known fact. This is the area of this triangle. Oops, like that. And now what might we can in fact estimate this area now, because we know that if these vertices here go to the boundary, we end up with something like that, which is called an ideal triangle. Oops, not good. That. Maybe like that. And we know the area of any such ideal triangle is exactly pi. So we get an upper bound of pi for all these co-cycles here. And so conclusion is that this co-cycle in continuous group cohomology is actually bounded, right? Just from the hyperbolic geometry of the Poincaré disk. And it thus defines a bounded cohomology class, which is called the bounded Kähler class. We denote it by kappa d. It's the class of this co-cycle in the second continuous bounded cohomology. And yeah, so the upshot of all this is that the second continuous bounded cohomology of SU11, real coefficients, is generated by this Kähler form. And this will later be of particular importance for defining certain invariants. Okay. So the next thing I'd like to discuss is, so now we have, we've seen here that all these co-cycles have as upper bound pi. And now the question, or it's natural to define or to consider these upper bounds in a more systematic way. And this can be done by introducing what is called the Gromov norm of these classes. So the Gromov norm of a class in the in degree k now. Now we pass the general degree now. So in bounded cohomology is the following. So it is the infimum over the suprema of all co-cycles in degree k in continuous bounded cohomology, so co-cycle, that represent the class alpha, right? And as we've just seen, an example is the bounded scalar class, which has Gromov norm pi, right? And it turns out to be very difficult to compute these Gromov norms, and they are in fact only known in very few cases. So these Gromov norm has been computed for the scalar class, not just in degree 2, but in arbitrary dimension for the symmetric space. And it is known for the product of the scalar class, I think, with itself in SL2 cross SL2, SL2R cross SL2R, and for a certain volume forms. But in general, it's not known what these Gromov norms are. But nevertheless, it's enough to know the Gromov norm of the scalar class in order to produce invariants of surface group representations. And this works as follows. So we have so we now define these invariants and study these Milnor-Wood type inequalities. So Milnor-Wood type and the presentation, or this definition I'll give today, follows Burger and Yotzi. And it generalizes results of Milnor, of course, Milnor and Wood, and Domit and Toledo. Okay, so how does this work? So we fix the following group, the following Hermitian group. We've seen already this group, SU11. And we recall that, just for notation, so the upper half plane is following quotient, and the Riemann surface is then the quotient of H by the action of the fundamental group gamma. And the first thing we need is, so the following fact: there exists what is called a bounded transfer map, which goes from the bounded cohomology in degree 2 of the lattice gamma. So this is now a bounded cohomology in the sense of original sense of Gromov, because gamma is discrete, into the second bounded cohomology of the Lie group H. And this transfer map, so I can't really explain in full detail where it comes from, but it's, roughly speaking, it's defined by averaging over this quotient here. And this is possible because gamma is a lattice in H. Okay. We can now take this bounded transfer map and combine it with the map on cohomology induced by the representation rho itself we started with. So the representation rho, it induces what is called the bounded Toledo map. So it's defined in the following way. So it depends on rho. It goes from the second bounded cohomology of the target Lie group G by functoriality, pull back along rho goes into the second bounded cohomology of the lattice gamma. And now it's clear why I introduced this transfer map to go on from this here back to the world of Lie groups, Hermitian Lie group. So we come to the second continuous bounded cohomology of H. And so one more thing. We know by assumption that the symmetric space X is Hermitian. So it comes with a scalar form omega X, which is a G-invariant 2 form on X. That. And so very much the same way as we saw it in the example of the Poincaré disk over there, right? It's just in higher dimension now, but the principle is exactly the same. But it's no longer true, I think, that the continuous bounded cohomology of G is one-dimensional, right? But we don't need this. We just need the scalar form here, and for convention we have to normalize it. The scalar metric on X normalized to holomorphic sectional curvature constant to -1. And now we can compare. So now we apply Van S again, and we get the corresponding scalar class kappa X, which is in the second continuous cohomology of G, and by the Burger-Monod result, we know it's also in the second continuous bounded cohomology, so it's actually a bounded class. But this was already known to Domich and Toledo, and also Clark Ørsted, who proved it. So Domich, Toledo, I think they proved it for the classical Hermitian groups G, and Clark Ørsted proved it for arbitrary Hermitian G. And now we are ready to define the invariant. So here's a definition. It's due to Burger, Yotzi, and Toledo. So this was some time ago, and this is very recent. So the Toledo invariant T of rho is defined by the following relation. So we take the bounded scalar class on the symmetric space X, and we apply the bounded transfer map to it, and it sends the bounded scalar class, which lives here, to a class in here. But since H is SU11, we've seen before by this example that this is just one-dimensional, so we can compare this image to the bounded scalar class on the Poincaré disk. It's a certain multiple, and this multiple here is exactly the Toledo invariant. Okay, and this is in H, which is one-dimensional. Okay, so what is this invariant good for? It's so there's a theorem. So in this generality, it was also proved by Burger and Yotzi. But in the case of, I think, Toledo proved it for SU-N1, so rank 1 case, and also Milner and Wood, of course, had it in very special cases, I think SU-11. So they proved that the Toledo invariant is the absolute value of the Toledo invariant is less or equal to the real rank of the Lie group G. And this is what is known as called the Milner-Wood type inequality. And it has a concrete geometric meaning. So we can ask, for instance, it is known that this invariant takes only integer or discrete values. So So you can ask, for instance, for the component in the moduli space of representations for which this inequality here becomes an equality actually, which is known, right? It's a sharp inequality. And these are called the maximal representations, and they enjoy nice geometric properties. They are discrete faithful and some more properties. And it was observed already by Goldman that in the case of SU PSL 2, these maximal representations exactly correspond to Teichmüller space. And so this inequality here has a concrete geometric meaning. And the proof is rather simple now, and that's I will give it because this is philosophically one of the main points of my talk. So as I said, Domich and Toledo and Clark and Ørsted, they proved that the Gromov norm of the scalar class here is in general pi times the rank of G. And in our example before, the rank was 1, so it was just pi. And the next fact is the bounded transfer map is norm decreasing for the Gromov norm, which is kind of obvious because, where is it? It's gone. No, here it is. It by pullback. So pullback just means the norm can go down, and the transfer map here is by averaging with respect to a probability measure. So it's not a surprise that the norm is not going up there as well. And now we can prove this inequality. So just by plugging in what we have so far, and so we get okay, so it's rather simple to get this Milnor-Wood type inequality once you know the Gromov norm, right? So okay, so as I said at the beginning, the goal was to compare these bounded cohomology results with the Higgs bundle results. So this is the end of the bounded cohomology story in this talk, and now we have to go to the other side to Higgs bundles. So maybe you can put this here. So the first step is what we have to do now is to express this Toledo invariant in terms of differential geometric data. So we can express the Toledo invariant in terms of the scalar form omega x in the following way. So we take the universal covering of M, so we've seen this before, we now denote it by pi, and we take a smooth map, a smooth row equivariant map F from this universal covering, which is just the upper half plane in this case, to the symmetric space G mod K, and such maps, they are not unique, but they exist because the symmetric space is known to be contractible. And then we have following lemma due to Burger and Yotzi, and it says that the Toledo invariant can be computed by 1 over the volume of M times the integral over M of the pullback of the Kähler class along F to M twiddle and then push down to M. And this is possible because F is row equivariant and the Kähler form is G invariant. So everything works out. And so this is the first step. This formula is the first step towards the differential geometry of the Higgs bundles, because now there's no bounded cohomology anymore. So it's just the pullback of the scalar class and the integral. And so we can now So in order to get this this non-abelian Hodge correspondence working, we have to make an additional assumption on our representation. So we have to assume that rho is reductive, which is a technical assumption, and it means that the Zariski closure of its image is a reductive subgroup of G. And now we get a Higgs bundle via non-abelian Hodge correspondence, right? And I'll now explain the main steps getting from this representation to the Higgs bundle. And this works in the following way. So So the first step is to construct what is called a G Higgs principal bundle, which consists of a principal bundle and a holomorphic structure and a certain section of certain associated bundle, vector bundle. So first we need a result due to Collet. He proved that there exists a harmonic rho equivariant map F. Right? Into X. So not just smooth like over there, but harmonic. And here is where reductivity of the representation is needed, I think. And so we have a gamma bundle now, the universal covering, and we can associate the representation to this and get a G bundle, PG, which is just M. So it's the fiber product of, no, it's the associated G bundle to this representation. And now I have to erase this here. And so F induces now a K subbundle, PK of PG, basically by reduction of structure group. So it's known that any such map here corresponds to a reduction of structure group, and this leads to this K subbundle, K principal subbundle, and we define our desired principal bundle as the following K. So we take the complexification of this maximal compact subgroup, and we get this here, right? So this is the first part, and now I have to explain where the section comes from, and okay. So first we observe that the bundle PG is flat. This is just because it's a discrete quotient of a flat bundle, the trivial bundle. So it has a flat G connection, which I denote by A sub G. It's a one form on P taking values in the Lie algebra, and it's induced by the Maurer-Cartan form on the Lie group G. So which I say like that. Right? And just by pullback and pushing it down. And now we've already seen the Cartan decomposition of the Lie algebra into K and this part P. And now since this connection here takes values in G, we can also decompose it into two parts corresponding to this decomposition here. So AG can be written as a K, which is a K connection, plus some error term. So here AK is a connection on the bundle PK, on the K principal bundle. Oops, taking values in the Lie algebra. And this theta is a one form on M, taking values in the associated vector bundle by the adjoint representation of K on this P, right? And And this here is also known as the real Higgs field. So, and all I want to say is to give those who don't know this, where this Higgs field comes from, right? It comes from this flat connection, which splits up according to this decomposition here. And then we define our desired Higgs field by taking the complexification of this Higgs field and taking the 1,0 part of it, which you can do because we are on a complex manifold, right? And this Higgs field takes values in the complexification of this Lie algebra P. And this is the Higgs field. Okay. And so then Sampson proved that since F is harmonic, there exists a holomorphic structure on P such that which annihilates this Higgs field. So the Higgs field is holomorphic, and moreover we get that the super Lie bracket of the Higgs field vanishes. Right? So this is 0. And this is the Higgs field. And these 3 boxes, they give the data of a Higgs principal bundle. And so the next step is to pass from this Higgs principal bundle to a Higgs vector bundle. And this works as follows. So we get a Higgs vector bundle. I denote by E and theta. So we have to fix a representation sigma of our Lie group G into some GL of some vectors, some complex vector space E. So we now, and this induces a representation of KC just by complex extension, and also an infinitesimal representation of PC into N, the endomorphisms of this vector space E. And now we can define the desired bundle, which now depends on rho and on sigma. So we define it as the associated vector bundle, right, to this representation sigma. And composing this d sigma with the former Higgs field. And we get a one form, 1, 0, on M, taking values in the endomorphisms of this vector bundle. And it's not a surprise, it turns out that E is a holomorphic vector bundle, theta is also holomorphic, and it satisfies this equation here. And again, this is the data of a Higgs vector bundle. And now our goal is to express the Toledo invariant we defined before in terms of the data of this Higgs vector bundle. And it turns out to be convenient to make the following definition for this purpose. So we recall that the complex structure on the symmetric space X, G mod K, is given by some. So this is the complex structure. It is given in the following way in terms of Lie brackets for elements in P. So this is because the tangent space of X at 0 at the base point is isomorphic to P because it's G mod K, so the K Lie algebra part vanishes, goes up. And okay, for some unique element J in the center of the Lie algebra of K. And I'll give an example in a minute. And so we assume this for now, and then we make the following definition. The representation sigma g into GLE is admissible if it's faithful and if the vector space E splits as V direct sum W for subspaces such that the following holds. The sigma of I is I over the dimension of V plus dimension of W times, so in matrix notation, dim W times identity matrix on V, identity on V, dim V, identity on W. So where does this come from? We see it from the following example. So turns out this definition here of admissible representation is modeled on the standard representation of SUPQ. So if we take G to be SUPQ, the standard representation, sigma G now goes into GL CP plus CQ. And in this case, the complex structure on the corresponding symmetric space is given by the following element: I over P plus Q times identity matrix on CP and minus P times identity matrix on CQ. Right? And it turns out, or our impression was that all examples of the classical Hermitian Lie group studied by Bradloff and his co-workers, they all use, for getting the Higgs bundles, these admissible representations, right? So so it turns out to be convenient for getting nice formulas, and here are these formulas now. Here. So, first of all, once we have fixed such a admissible representation, it turns out that the vector bundle E splits as the direct sum of two holomorphic subbundles, and the Higgs field is of the form 0 beta gamma 0. For beta is a one form taking values in hom VW, and gamma takes values in hom, WV VW, right? And okay, and now the theorem we proved using this the following. So the Toledo invariant can be expressed as 2 pi over the volume of M times a certain constant times the integral over the first Chern class of the bundle V, right? And so this is just the degree of V, and it's a fact because the bundle PG was flat, and so E is flat, so the first Chern class of V is negative first Chern class of W, and maybe I can put this here. Can people read? Yeah. So the constant C sigma, it depends on sigma, and it's obtained by normalization in the following way. So we take the scalar class at the base point, plug in two elements in P, and it's known all these two forms on X are multiples of each other. So we can fix a constant to make it equal to the trace of d sigma I times d sigma X, d sigma Y minus d sigma Y, d sigma X, right? In this way we get this constant here, just out of the properties of this admissible representation. And so just a word about the proof. So we just plugged in all this, we plugged in this lemma, well, this lemma here into this mechanism going to the Higgs bundles, and then we applied Chern-Weil theory to get this result. And so an immediate corollary of this is now the corresponding Milnor-Wood type inequality, we just have to plug in this formula into the Milnor-Wood inequality. So we get 2 times the rank of G over this constant times genus minus 1. And a new feature of this is that we have this Milnor-Wood inequality now uniformly for all Hermitian Lie groups G. Not just for the classical ones like in the literature before, also for the exceptional ones, for instance. I mean, in principle, the only thing you have to determine is this constant here. And in an example, so we take SUPQ, it turns out that the rank of G is the minimum of the numbers P and Q, and this constant is minus a negative 2. So we get the Milnor-Wood type inequality following form. And this is exactly what Bradloff, Garcia-Prada, and Goten obtained by their study of Higgs bundles. Okay, so this was now the transition from bounded cohomology to Higgs bundles. And I'd like to close for the last 5 minutes with some ideas about possible generalizations of this mechanism. And okay, so it is a well-known fact that all this works for not just for Riemann surfaces of genus at least 2, but also for in higher dimension for complex hyperbolic manifolds. So, and in fact, all this here can be immediately generalized to this. So the first generalization is so we can take M to be quotient of hyperbolic n space, not just n equals 1. So it's an n-dimensional complex, compact hyperbolic manifold. And in this case, we get the it's still here. Okay, so in this case, the formula has to be modified by adding a certain power of the Kähler form, right, to make this top degree form. And for these formulas, we also have Milnor-Wood type inequalities. And this reproduces results obtained by Higgs bundle techniques by Cosiaris and Momo. Right? Okay. And now, once you have a base of higher dimension, not just one, the obvious question is: this is just the first Chern class. So, but now it's possible to think about other characteristic classes of the bundle, right? Because the base is no longer one-dimensional. So, the question is: what about higher degree characteristic classes? Of this bundle V, and the key to these to treat this question is the following theorem, which goes back to Gromov, and later in a slightly modified and generalized version to Bucher, Carlson, and then back to Hartnick and myself. And it says that the comparison map we had at the very beginning of the talk from the continuous bounded cohomology of any Hermitian Lie group into the continuous cohomology, it is onto for all Hermitian Lie groups, right? So this proves part of this main conjecture for Hermitian Lie groups. It's just the surjectivity part. And an immediate consequence of this is that now any class alpha in the continuous cohomology of G yields what we call a higher Toledo invariant, right? We denote it by T rho alpha. And if we compare it to what we've done before, there we had to restrict to degree 2 because it was only up to that time only known for the Kähler class to be bounded, right? But now with this result, we can take any degree classes. And we can play the same game, and we get the following result. Okay, so can you give me another 3 minutes maybe with that? Okay, thank you. So we get a Milnor-Wood type inequality of the following form. 1 over p times the Gromov norm of this class alpha. So at first sight, this looks like nothing because now we know we have an inequality, but we don't know this. Because our result about surjectivity doesn't say anything about the actual Gromov norm. But still, we have this inequality, and we can ask for the corresponding Milnor-Wood inequality for the bundle V. And so we were only able to carry this out in a particular case. So we take SUPQ, and we take a class alpha k in degree 2k in the continuous cohomology, which by Van Es was 2k degree classes on X invariant, and we can give an explicit formula for this class. So it's a straightforward generalization of the right-hand side of this this lower equation over there for determining the constant C sigma. So it looks like the following. So this element, and then we have the alternating sum over, with a sign of the product of these elements in the Lie algebra. Maybe 2k. So these live in P. And in this way, we get the following formula, which was quite surprising. So the Toledo invariant now for these classes here, these classes in in Lie algebra cohomology, but in continuous cohomology, it yields the following formula. This unknown constant here, which comes from this Gromov norm, but interesting term is here. So we get the kth degree part of the Chern character of the bundle V times power of the Kähler class. So this is an example of what happens if you work with these higher classes. And it suggests that we have inequalities for probably all for characteristic classes, for any characteristic class of V. This should be understandable, I think. And and the concluding remark is now, as you see from the diagram we started with, there was this arrow from bounded cohomology to Higgs bundles, which has now been, illustrated by this formula here. And the question is, can we go back, right? So far, all the information came from bounded cohomology and was applied to Higgs bundles to reproduce known results. And the answer is maybe yes, because the question is, can we compute this Gromov norm? And it's, as I told you, that it's really hard to compute it directly, right? And the question is now, can we use the corresponding inequality on the Higgs bundle side for the Chern characters to get some information about this Gromov norm? Just because it turns out that, all you would have to do is prove Milnor-Wood type inequality for the Chern character, which is sharp, right? And then compare it to the Milnor-Wood type inequality coming from this mechanism here, and combining it with so this gives a lower bound for this unknown class. And it turns out to be quite, at least doable to compute an upper bound for this class because, as you probably remember, it's an infimum over the suprema of all representatives of the classes, right? So it's difficult to get a lower bound, but it's not so difficult to get an upper bound. So, and if it turns out in the end, or this would be the hope, that the upper bound we get from the direct estimate on the cohomology side coincides with the lower bound we get from the Higgs bundle consideration. And then we would have a formula for the Gromov norm. This would be one possible application in the other direction. Okay, thank you very much for your attention.
Any questions?
If you, for your UPQ you take UN1, you have
Sorry?
I mean, can you conclude something about the Gromov norm in that case?
In which case?
When the target group is also complex hyperbolic space. I mean, when one of P or Q is 1.
You mean rank 1?
Yeah, in the rank 1 case.
No, it doesn't make it easier. Oh, you mean it fails because the is that your question?
Yeah, right.
Yeah, that's true. I should mention, or I should add that at least, well, it's not obvious. If P and Q are the same, so in the tube type case, this is like more or less like I described. But if one of these is 1 here, then this bundle V, or say if P is 1, this is just a line bundle, and there are no higher characteristic classes. And in this case, I think it's not, at least not literally as I said, but maybe there are some methods to reduce to tube type. Yeah, but it would already be good to have a result in the tube type case, I think.
Any more questions? In that case, can I thank the speaker again?